We'll now begin Module 1, Seismic ABC Design Requirements. We're pleased to introduce our speakers, Bijan Khaleghi, State Bridge Design Engineer with WSDOT, and Nikzad, Principal Engineer with TranTech. Bijan?
Good morning. Welcome to ABC in-depth webinar, latest Seismic ABC application. This is Model 1 by Dr. Khashayar, Nikzad, and myself, Bijan Khaleghi from Washington State DOT. We're going to cover LRFD bridge seismic design requirements, ABC seismic research and implementation, innovation in bridge seismic design, and precast cap design example that will be offered by Dr. Nikzad. So as we talk about the ABC and seismic, the connection is becoming more important, most important part of that, because this is within the load path of transferring the lateral forces into the substructure and foundation. So we want to have the connection that are constructible, that are seismic resilient, and also have a long-term performance and longevity. Commonly, we are all familiar with emulative construction type. Those are the cast-in-place type that has been used for years. But when we get to ABC and precast, so that's becoming a challenging how to have the connection that does emulative type of construction behavior that's prescribed in the code. And we are also talking about the innovative connection types that are used for meeting the seismic resiliency and functionality after major earthquake. Those are socket and pocket connections, super elastic materials, and self-centering bridge piers. So there are two common code that's used. One is the LRFD bridge design. That's a force-based design for seismic part of that. And also there is a LRFD guidance specification for seismic. That's a displacement design. That's commonly used in state seismic states. And also recently we have a LRFD guidance specification for ABC construction. That the second model is going to go through that, and that model bring all the latest on seismic design for ABC and connection to your attention. Besides the actual LRFD, there are also other seismic challenges that should be considered. In the Pacific Northwest, we are dealing with Cascadia subduction zone and M9 earthquake, and also basin effect that is not covered in the code with the 2014 map that we are using is not addressing the basin effect, but new generation of maps will be including that part. We are also dealing with safe liquefaction as well as local fault and so on, that we are each state and each region has its own particular seismic consideration. So this picture just shows actually why we are doing that, because the seismic design is essential for bridges. Is an extreme event, doesn't happen every day, but when it happens, we got to be ready for that. So that becomes a continuity in the superstructure. That's very important. Good foundation design, good joint design, shear design, and overall structural behavior to ensure that we have a consistent load path from the super to sub to resist the earthquake. So in order those things doesn't happen, so actual guidance specification, they have recommendation on the structural type and how to have a structure that's a seismic resilience. And some of those are permissible, and some of those permissible also with approval. But the one on the right side, those are not recommended for bridges. Those are that we are getting yielding or liquefaction or plastic hinging away from the zone that we can control and we can provide immediate repair and so on. So in order to get to the seismic resiliency and also meeting the ABC requirements. So the very first step that we did in Washington was doing some precast connection. And we started with the grouted duct connection by University of Washington, Dr. Stanton and his team. That followed by Highways for Life, that is will be doing the component test, the connection test, and as well as column, precast column to shaft and precast columm to spread footing connection. So these are a research project that has been completed in Washington State and has been implemented, and also is partly covered in the ABC specification that will be coming up. So the key to seismic performance, whether we are using a precast or cast in place, is to meet the ductility requirement. Ductility requirement means once we get to yielding, we still have post-yielding capacity without losing the capacity. So that's the moment curvature that it shows. We passed the initial yielding, but this is the two stage and this plateau that shows us we are still meeting the demand requirement whilst we are going to significant inelastic behavior. And this is actually ductility that we are designing for, whether ductility is 4, 5, or 6, or so on. And the slide on the right, it shows the same columns. If it's not properly detailed and constructed, so we may have either brittle type of failure or either having the strain degradation and so on. So either one of these is not acceptable. We are this is a loss of capacity that we are dealing with. So actually also guide specification provides the cap longitudinal direction for capacity protected member adjacent to plastic hinging remain essentially elastic, and the requirement is that they got to meet the principal compression and principal tension stress limits. That's specified in the H2L RFD specification, and also the shear stress within the joint zone. So this joint remain essentially elastic by having consideration for principal stresses. And that's also from the guidance specification, the zone affected by this transfer of plastic hinging that's happening at the top of the column, and how this section should be designed in order to meet the requirement of capacity protected. Essentially, we are designing that area for 1.25 times of the moment demand. Also, there are code requirements for P delta effect that become very important when we are dealing with especially the ABC type application, because the joints are critical. So we want to manage to keep the moment going through the joint to limit. So there is a 0.25 MP that's considered for reinforced concrete column and 0.25 MN for a steel column. Also, there is the axial load, which is important because when we go to the rocking due to the seismic, so we don't want to have heavily loaded columns. So the code is requiring the 0.2 F' CA. And most importantly is the balance stiffness concept for frames and bends and columns. This is in the code is considered as optional to be considered, but we are doing that as a requirement because that's good to have a equal or close to equal distribution of lateral forces on the substructure elements. There are also guidance in the code for type 3 that's remaining considering elastic substructure and elastic superstructure, but having a fusing system between the two. And this is using different type of isolation bearings that is being commonly used, and also allows to lengthen the period of the structure in order to get a longer period and reduce the spectral acceleration, basically reduce forces that's going to be considered. So in Washington, we also have consideration for earthquake functionality after post-earthquake functionality and serviceability. So that means after a major earthquake, we still have roads open for limited service or full service, depending what level of ductility that we are allowing over there and what level of functionality that we are looking for. Is a limited service or full service, etc. So the current seismic design in H2L RFD is a normal, which is a no service after earthquake, but is a no collapse, is a life safety. So we are going beyond, and we are going to have we are considering here as either limited service or full service for either essential or critical bridges. And these are the ductility limit that we adopted for these essential and critical bridges as compared to normal bridges. So by increasing the demand, having better handle of post-earthquake functionality, we acknowledge there are other ways than conventional design and going to the ductility that going to life safety. So these bridges in that zone are not going to be functional after the earthquake, so it's got to be between essential. So designing for seismic is possible, but is sometimes not practical and very costly. So we are looking at other options here that the next few slides I'm going to talk about, while we are meeting the seismic demand rather than having the conventional plastic hinging on top and bottom of the column. We are looking at the rocking option. So we have, which is more suited actually with precast column and ABC. So we go through this rocking, but that after the earthquake is coming back to the original position. So basically we are able to use the bridge after the earthquake for service condition for functionality. So as compared to this one, so we are not going through this post-earthquake yielding and eventually failure, but we are remaining within that area that bridges are usable. So one of these concepts that have been used is using a shape memory alloy in column. This is material along with the engineered cementitious composite that provides self-centering that goes to the super elasticity post beyond the initial yielding, but after unloading is coming back to its original position, is basically close to zero residual deformation, and that allows this taking the seismic motion while it's coming back to the original position. That was tested at for a washout project, was tested at the University of Nevada, Reno by Dr. Saidi, and the first bridge of this kind was built in Washington State and is open to traffic since last February at the Alaskan Bay Viaduct South entrance. The other option that is looking is a self-centering with the rocking consideration, and that one has the center post-tensioning that, as you see, the rebar that are designed for taking the loads that could go to the yielding and come back to original position. But what keep the system working is the strands that we have is a center PT that's unbonded, and that goes through the rocking and coming back to the original position. So the total system is a combination of rebar and strands, but we are getting back to the zero deformation and then to the self-centering concept. So the key to this kind of design is to keep strands very elastic, so stay elastic, provide the recenter that's about the range of 30 to 50% of FPU. So we don't go beyond that because we don't want strands when it goes to the rocking, it yields. So the other thing that we have a hard point at the bottom of the column, bottom and top of the column, and that requires some armoring lower part of the column in order to prevent the damage to the foundation and to the end of the column. So in that case, this confinement can is a solution to that one, and also similar concept for the top portion with the grotted duct. Other option, we have one model 5 is talking about the CFST, concrete filled steel tubes, but there are the option with that one. We can bring it to the ABC. In that one is using a dual shell columns and having in the center PT bar, unbonded PT bar. Again, like previous slide, we are getting some kind of behavior from the steel part of that, but the self-centering provided by pre-stressing allows to have a combined behavior that with zero residual deformation and back to functionality and serviceability as desired for that one. The other concept that could be used is along work that has been done at the Florida International University by Dr. Azizi Namini, and that was the use of ABC, use of the UHPC in the column within the plastic hinging zone, and that one has successfully done, tested, and beyond. So what we are considering is using the shape memory alloy within that plastic hinging zone to bring the self-centering and seismic resiliency. So these both has been tested in a different place, different reason, and a bridge is built with shape memory alloy. So this is the next step that we are looking forward for that one. And also by increasing the seismic demand and expectation for post-earthquake functionality and serviceability, we are also have a tool in the toolbox, and that's the concrete filled steel tubes. That's going to be presented later on, and that give us more seismic resiliency for foundation and below ground. With that, I pass it to part 2 of this presentation by Dr. Nikzad, and he's going to talk about the precast concrete bend cap design example. Thank you.
Thank you, Dr. Khaleghi. Again, good morning, everyone. Could we go to the next slide, please? Okay. So in this segment of Module 1, we will present you with a cap beam design as part of the overall ABC approach to bridge construction. The example is courtesy of Mr. Tanaraj Patisek from Oregon DOT, and is part of an upcoming state-of-the-art PCI report on seismic design of precast bridges. This example dovetails nicely to the upcoming modules 2 through 4. As a general practice, again, in this slide, you're looking at a hypothetical bridge and a construction sequence with ABC elements from bottom up, and our focus will be the capacity protected design of the precast cap beam. In general, we try to capacity protect the elements of the superstructure, which we call them CP. It's in the new ABC AASHTO guidelines that is out, revision 1, as Dr. Khaleghi showed in his slides. And also we try to confine the energy dissipations to the elements of substructure, specifically the columns. Next slide, please. The example that we're going to be looking at is a three-span bridge with equal spans of 124 feet 8 inches, and there are 2 interior bends supported by 2 columns, and we're going to show the design of the cap beam in the two stages in the ensuing slides. Next slide, please. As seen, the first stage bend cap design includes a precast U-beam, and you have the and stage 2 of that will be basically a composite section that includes the interior pier diaphragm and part of the deck slab. And we need to look at the different forces at different times associated with this design. Next slide, please. Stage 1 basically in this slide is presented where first we are presenting the non-composite sectional properties of the precast U-beam, and also the composite properties of the U-beam where the cast in place concrete is poured in there. Next slide, please. Stage 2 are the sectional properties of the full section that includes, as I mentioned, the interior pier diaphragm and part of the deck. Next slide, please. For the non-composite section, basically at stage 1, we are looking at basically the U-beam has to carry its own weight, obviously, and also the wet weight of the concrete that is going to be poured in there. And as you can see, this the flexural demand and capacity with some nominal reinforcement is met in that stage. Next slide, please. For the non-composite section, we also need to go through the shear capacity and shear demand, and these are standard AASHTO LRFD equations that basically, again, with nominal shear reinforcement, the shear demand for this stage is met. Next slide, please. Next, we'll go to the stage 1 composite stage where the concrete within the U-beam has hardened, and it can be used now for the erection of the girders on top of it. The loads that this stage 1 or the lower half of the cap beam needs to endure are obviously the girders, the slab hunch, interior diaphragms, and then we'll go again look at the our flexural demand and capacity. We see that, at least for this example, there will be no need for any bottom reinforcement, but we need to add additional number 5 bars in the slab area to ensure that the negative moment demands are met. Next slide, please. Okay, and then as far as the shear capacity and demand is concerned, again, this is standard AASHTO approach. We got to go to AASHTO LRFD 5.5.1.2, where the B and D regions are described. D regions are the regions that are close to the supports or force discontinuities, where basically Bernoulli type beam theory does not apply, and AASHTO in those situations basically recommends using the strand on tie method. That is an approved method. We're not going to go through this method here for brevity and for the basically with respect to the geometry of the cap beam that we have in this example. The whole cap beam can be designed as a D region, and the strut and tie method can be used for that. Also, we need to look at the interface shear between phase 1 and phase 2, which we'll be talking more shortly, and crack control and torsional capacity of stage 1, because the contractor may elect to erect the girders on top of stage 1 cap beam one span at a time. Then you will have some torsional demand as well. Next slide, please. After the composite state of stage 2 has arrived, obviously we will look at the demands at that stage, which will have the barrier future overlay or DW forces. And also, this is the stage that live load analysis needs to be made, and basically strength 1 load combination needs to be looked upon. And these are the demands from this load combination. Next slide, please. Also, stage 2, we need to look at the extreme event demands, and normally in this stage we'll do a multimodal elastic seismic analysis or response spectrum analysis, and we do that via obtaining some seismic parameters from our geotechnical engineer, which are shown in here. And then we'll do the RSA analysis or the response spectrum analysis in 2 orthogonal directions, and we'll combine them per AASHTO load combinations, which most of us are familiar with, which is 1 times the longitudinal directions, plus the 0.3 times transverse, and the other load combination is 0.3 times longitudinal plus 1 times transverse direction. And then we'll make those load combinations, and we'll find the governing flexural demand. Next slide, please. The flexural demand needs to be compared with, and this is the elastic flexural demand, needs to be compared with the plastic moment capacity of the column, and AASHTO allows the lesser of the 2 to be used for the capacity protected cap beam that we are designing, and in this case, elastic forces is the lesser of the 2. And again, analyzing the section that we had, we realized that there's no need for any additional rebar at the bottom for the positive moment regions, and for the negative moment regions, we need to add 6 additional number 7 bars in the bridge deck and within the zone of the cap beam that we are designing to meet the demand that we are facing. Next slide, please. For the shear capacity and shear demand, although we could use the elastic forces, which are the smaller of the 2, it is normally a good practice to use the overstrength moment and the shear associated with that, and that's what we have used in here, and we can calculate that the shear demand for overstrength is 659 kips for this example. Next slide, please. Now we go through the standard shear design, per AASHTO, and we look at the amount of shear stirrups that we need, and we are providing 2 legs of number 6 at 8 inches each that goes through the whole cap beam, and we'll calculate that, and we are seeing that our capacity is 944 kips. Which satisfies the extreme 1 demand at this stage for shear. Next slide, please. Again, we have to go back and do the overall analysis of the cap beam for strength 1 limit state, and again, you can use strut and tie method for that, and you also have to do some crack control reinforcement, the checks. And also at this stage, you have to look at the positive moment reinforcement extension due to basically reversibility of the seismic forces on the full cap beam section that we have. Thank you very much. That concludes our example. And again, sorry that I went through the slides very quickly due to time limitation, but all the details will be provided to you following the presentations. Thank you.
Okay, that concludes Model 1, and I pass it to for any question that Kash and I could handle.
Okay, thank you, Bijan and Kash, for your overview of the Seismic ABC design requirements. We'll now begin the Q&A session. We had a number of questions come in from registrants about the availability of the slides and comments on what participants would like to see in the modules. We'll follow our usual procedure of posting the recordings of each module and the PDFs of the presentations in the in-depth web training archives on the ABC UTC website. I'd like to now turn it over to Paul Lyles, former Georgia State Bridge engineer, who will be moderating the Q&A session, assisted by Ahmed Abu Hawash, Chief Structural Engineer with the Iowa DOT, both of whom are members of our ABC UTC Advisory Committee. Paul?
Okay, thank you, Mary Lou. We did have a few questions that came in beforehand, and we will go on and ask those. The first one I wanted to say is the question came in, are you aware of any actual applications of the precast U-beam construction for the caps? And Bijan showed a bridge that was built, and I just wanted to make sure if that one used this type that you went through in your example.
Yes, that have been used. For main load carrying, the precast U has been commonly used. But the function that we are looking here, that was presented was for the cross beam and an ABC that using precast U on top of the columns and filled with the concrete. So we have done that. Yeah, that has been used in different locations.
Okay, in Washington. Okay, that's fine. Then a question came in about can the structure, the design example we were given, can it support a magnitude 8 earthquake?
I believe so. We designed for the seismic design requirement as specified in the actual RFD specification, and that's the design earthquake with the location, with the magnitude, as well as the soil amplification that we are getting based on the site that the bridge is located. So the design is meeting the actual specification.
Okay, I know the soil is very important when you're doing the applications for the seismic thing. So that's good. Then how different would you say the seismic design is from if it was not seismic design? For how different is the seismic design if it's not ABC? Let's say it that way.
Seismic design for the older bridges built prior to 90s. The seismic design came out in 1983 for the first time. And all those before that does not meet the seismic design requirement, and mainly for the foundation and also the connection between the substructure and adjacent member, either foundation or superstructure, and the lack of the confinement and also lack of the plastic hinging capacity. So those are the main things. That's what each state, including Washington, we have our retrofit program going back to those old bridges to bring them back to no collapse requirement to meet the deficiencies that those bridges have with the lack of seismic design.
Okay, we're just about out of time. I want to ask Ahmed if there's any questions that have come in that we want to pick up. Ahmed?
Yeah, Paul. I haven't seen any questions come in so far.
Okay. Well, it is
one comment
11
now.
Okay.
Paul, go ahead and ask this question. Are there any examples in service for self-centering columns?
One thing that we built recently, a bridge that's shape memory alloy and super elastic material. That is in service. There is also a CHRP report on that one. That was a project. including design example, and also there are other examples of the self-centering with center post-tensioning that has been tested and used.
Thanks. Although we do have a few more questions, but I think we're running out of time. Mary Lou?
Yes, thank you, Paul and Ahmed. We're now at the end of the first 40-minute module. Thanks again to Bijan and Kash for presenting Module 1